Okay, let's continue with the section in this morning section of the school. And now Pablo Carrasco from the Federal University of Minas Gerais, he is talking about the Central Limit Theorem for non-regular potentials, please.
Okay, so good morning. It's a pleasure to be here. So let me start by thanking the organizers for giving me the opportunity to talk about my research. And I'm very happy to be in the 8th School of Brazilian Dynamical Systems. It's an honor. I'm going to tell you about some, well, the title of my talk is the Central Limit Theorem for non-regular potentials. This is based on results of a joint project which I have with Federico Rodriguez Hertz from Penn State University. And I'm going to start by giving you a disclaimer. I'm going to try to make my talk very basic. So the experts, they're going to excuse me. The idea for me is that this type of events should be addressed to students, right? It's a Brazilian school. So I'm going to tell you what I'm going to say today. I cannot start with anything more basic than the first question is I'm going to discuss what we understand by a dynamical system. Then I'm going to introduce some objects and I'm going to try to understand some statistical properties of that object. After that, I'm going to tell you some ideas of the proof of the result that I'm going to present. And if I have time, I'm going to give you a couple more slides. But my idea is to focus on the first 3 items. So let's start. So what is a dynamical system? And of course, that type of question, the answer is going to depend on who you ask, right? So if I ask this question in this audience, we are all very influenced by essentially 2 types of schools. First, the Ismail School, which had made a lot of advances in this theory. A representative of this school is Shakov. For that, I think that if you ask this question in Brazil, you are going to obtain something like the following. A dynamical system is given by, say, some Lie group action of a group, a Lie group in a space. For example, we take the integers and we look at the integers of a single map. And this is essentially, you understand that there is some well-defined evolution law. And what one does is studies topological, geometrical, or statistical properties. This is perhaps the last part is more relevant for the Russian school. Representative there is Sinai, that means Sinai, and also Pondrigan, and many others. So this is a type of answer. But there is another, perhaps older answer. So if you ask Poincaré or Gibbs what is a dynamical system, perhaps they will tell you something different. They will tell you, yes, there is an evolution law, but there is another additional object there, which is an observable. I should have written X. Right? So you have a real value function that you are going to, it's going to permit you to make measurements. You look at the temperature, you look at pressure, you look at volume, but this is part of your dynamical system. The only thing that you have to do, you are allowed to do is make measurements. So conceptually it's different, okay? They assume that there is a law, but the only thing that you're going to know is after you make some measurements. And the thing is that measurements have some problem, which is necessarily you are going to introduce some errors. Okay. Now here I'm not trying to go into quantum mechanics type of stuff, where you can describe your system or not. I mean, if you have your ruler, your thermometer, you are going to have introduce some errors. So this is what you are going to do. What you can really do is you assume some typical initial condition, and you make some measurements every unit of times, and you write the result. Okay, so if you have been into a laboratory, into a lab, a physics lab, this is what you do actually. And if you have been to a laboratory, you know that it's most stable to, instead of writing each number, you are going to write the cumulative sum of them and then take average, because you don't want to have some fluctuations. Okay, so I'm going to take Sn, which is, in principle, is going to be the sum of the measurements. And what will be the ideal case? The ideal case is if your process is given by some transformation from X to S, say homeomorphism, then your measurement is simply applying your observable at time I. And then what you are doing is summing over this. This is the Birkhoff sum, right, that you all know. So this is what you essentially are doing. Now, to make some progress, I need to make some natural assumptions. I'm going to assume that errors do not accumulate over time, otherwise I cannot do anything. Essentially, this means the following. I'm going to assume that S of n plus m in x is comparable to the sum of S of n of x plus S of n of Tn of x. This is following. So if this is n, and I make my measurements in m, wait, let me write. And this is m. Okay, so to measure from here to here should be comparable of going here and then starting in the corresponding point. This is Tn of x, and then all the way over. Okay, so this is the first condition. And then the other one that I want is that if I start with points which are essentially close by, then the sums do not differ much. I'm going to be precise in a second what I mean by that. So for this talk, you can assume that the dynamics is the shift in two elements. Okay? Or if you are more bold, you can assume that it's a mixing to shift of finite type. But say that this is a shift. And then this x to n are just the points which they are going to be close to x for n iterates. Okay? So if I fix a word in 0, 1, say 0, 0, 1, so I'm looking at the points which start with 0, 0, 1, and then whatever you want. So let me introduce a first definition. I'm going to say that a sequence of functions like that is a Bowen quasi-cycle if it verifies these two conditions. Okay? This, what you have to think, is the sum of measurements. Okay? Any questions so far? Good. All right. So here is a natural question that first one would like to understand. Say that you are given a Bowen quasi-cycle, this sequence of measurements. Do you really have a function that is giving that measurements? Is it really that you have a Birkhoff sum, which is, say, at bounded distance to these measurements? It's a definite law that you have. Okay, I'm going to use a weird word which doesn't seem to have anything to do with anything, which I'm going to say that they are homologous, because why not? So if you see, this question is a little bit subtle, because I'm saying that they are at bounded distance. I'm not saying that they are at close distance. I'm saying that it's just bounded. Right? So the function that I would like to, the function that I will obtain, in principle, perhaps it's not defined everywhere. Perhaps it's defined for typical points. Typical points means with respect to some invariant measure. And I'm going to say that a Bowen function with respect to this invariant measure is a function which is in L infinity and has the property below. If the two words coincide with n, the sums do not differ too much. If I want to be able to answer the previous question, necessarily my function has to be like this, because I assume that the Sn of x satisfy that property. So this is a simple consequence of the triangular inequality. Example of Bowen function, Helder functions, Lipschitz functions. Those satisfies this. Is an exercise that you probably have seen, or you can do very easily using that exponential contraction in the stable or exponential expansion in the unstable. So I'm going to go for the first result. The answer is yes. So if I give you a quasi-cycle, this sequence of measurements, then, and I give you an invariant measure, then you can find a function which tails the measurements. It's at bounded distance. The Birkhoff sums are at bounded distance of the measurements. And this is the second part. So if I have two such functions, these are homologous. They are at bounded distance from one of each other, if and only if there exists a function in L infinity such that the difference is a coboundary. It's a L infinity coboundary. And that holds if and only if for every invariant measure the integrals are the same. The dynamics is a shift here. There are parts which you don't require the shift. The second doesn't. The first, the existing part, yes, does. Or hyperbolic. Sorry. Now, let me make a couple of remarks. This is, there we go. This is a version of the Lipschitz theorem in L infinity. And then this part is a little bit subtle because in principle, my function depends on the measure that I have chosen. And then I want to integrate it with another measure. You can do that. You are going to believe me that you can do that. Okay? There is a well-defined way to integrate these type of functions for any invariant measure, even though they are defined with respect to another measure which may be singular with respect to the original one. And then the cohomology class, the Lipschitz cohomology class is defined either with respect to the periodic data, which is the equivalent to this, or the existence of a co-boundary. So this type of theorems, these type of questions, they were answered before assuming some regularity. They wouldn't say Bowen mentioned the function. They will say that your function, that your cocycle is, in some sense, I said that. Let me go back to this slide. I'm saying this equation only means bounded. The conditions that they were putting before is that this condition improves as any m go to infinity. And then you obtain a Helder function. But our interest, which I'll try to say something at the end if I can, are some geometrical objects which come from very non-regular processes, and then you, in principle, you don't have hope of obtaining a Helder function or anything like this. Okay? So I'm going to use this representation theorem for saying what I want to say afterwards. How much time did I waste on this? How much? ¿Cuánto tengo que tener? Tengo 30 minutos más. ¿Cuánto? One. Any questions so far? Is that the statement of that theorem clear? Yes. Sure. It is tied to dynamics. Yeah, and this part as well, right? This is dynamical. Can I go on? Okay. So, all right. So we have that representation. So we have these objects with, first we're coming with some, we're a bit. Mu almost everywhere. This inequality is mu almost everywhere. Yes. I know the boundary is going to change. If I change the measure, the invariant measure, now the u changes. And the function changes. So if you fix a measure, you can imagine that you have some projection. And then you solve the cohomology in that measure space. But then if you change, principle changes. So okay, so we have these objects, sums, and now we can essentially approximate by Virgo sums. So for example, say that I want to answer the following. So suppose that you're given a Bowen quasi-cocycle, and then somebody gives you the invariant measure. The theorem above shows that the limit exists almost everywhere. And here is the proof. So if this, since this is bounded by C, these sums differ by a uniform constant over n, and then you use Birkhoff. You know that this guy converges. And that's it, right? Okay, that looks cheap. Let's try to get something more interesting. So what we are interested in obtaining some more precise information of how this sequence behaves. And as above, we are allowed to look at the Birkhoff sum of a weak Bowen function, but now the problem that I'm going to have is that this weak Bowen function is not regular. Okay? Most of the things that you typically hear about when say, I'm going to be talking about the Central Limit Theorem. I'm going to explain what that means. But you may have heard the central limit holds for Helder potentials. That's assuming some regularity in your observable. I don't have it. So I'm going to try, and what I'm going to do is I'm going to reprove some version of the central limit theorem for non-regular functions. Okay? Now, I'm going to do the following. Again, you are going to forgive me if this is too basic. When I did my courses in Dynamical Systems, nobody told me what was the central limit theorem. For me, the central limit theorem was something with independent random variables and who knows what. So I'm going to tell you how do we think about the central limit theorem in dynamical systems, okay? Now, suppose that your function has zero mean. What does it tell you, Birkhoff? It tells you that S of n of the Birkhoff sum over n goes to zero, right? Say that the measure is ergodic even, okay? Assume that your measure is ergodic. So if I call this guy an, means that an over n goes to zero. That means that this guy increases slower than this guy. So in fact, it's little all of n. So if you divide by n goes to zero. So now the question will be, okay, can we put something in the denominator so we have convergence to something which is not zero? Right? Divide by n, this goes slower than this. But perhaps, I don't know, if we put something in the denominator, I get something better. Okay? And convergence in some sense, who knows what. Let's see. Now, if S of n of phi of x over an converges, we expect the quadratic error, the thing that you do when you do least squares, that remains bounded. This is the distance of this guy to its mean. The mean is zero by assumption. And you get this, right? You get an, the sum of phi, the L2 norm is the sum of n phi L2 over an squared, and you want that to remain bounded. Now you can compute Sn of 5 square L2 is simply n times the norm square of your function plus 2 times this sum n minus k, what says f should be phi. Here is also phi, okay? The correlation between the two. So you have this sum, so if you divide, if you, for example, you look at this formula, say, well, if I take a square root of n, I obtain this thing. Well, okay. So it looks like the reasonable condition, the reasonable assumption will be taking a square root of n for my sequence, because then the error is going to remain bounded. Does it make sense? Do you have questions? Okay, this has a name. Let me call the variance of your function this limit whenever it exists. It may not exist. But if it has, I'm going to call it the variance. Look at that, I'm doing over n because I took a square root of n. So the main theorem that I want to talk today is the following. So say that I have a Markov measure. I'm going to define it in a second what is a Markov measure. you can think of the entropy maximizing measure if you like, or you can think of Bernoulli if you like. Take a function in L infinity, which is a open function, and assume that it's not a boundary. Then sigma square of phi is different from 0, and this happens. The measure of this set, so this points such as S of n of phi over the square root of n divided with this normalizing factor less than or equal to c converges to this. This is a type of convergence. If I say that this is the weak convergence of measures in R, everybody agrees? Should I say something about this or not? So whenever you have if I have a sequence of probabilities in R, I'm going to say that this measures weakly to some measure mu if for every function bounded on R, so you have mu n of f. Conversion to me. This is a natural convergence, the real numbers. Continuous and bounded. This is equivalent to that. Okay, this is equivalent to that. It's equivalent that the cumulative distribution functions converges in continuity points. And what I have there is the distribution of some measure, which is the normal distribution. Okay? Oi? The variance is, which is not a boundary. The limit exists, yes. Yes. No. I don't have any degree correlation. No. I don't have any stimulus. That would be great. No, the series was, I don't know. In fact, I don't know if the series converges. It converges in average, but doesn't converge in general. You mean this series? This series converges. But not the, okay. Now, so you have some additional things that you can say. For example, you have some pretty good estimates of how the Birkhoff sums are greater than some delta. This is the case exponentially with respect to some constant, and then you also have it for the square root of n. Okay, so this is called the case of large deviations. And if you know what I mean by this, the functional limit theorem and the law of iterated logarithm also holds. Okay, so this is the theorem that I want to discuss now. Any questions? I'm sorry, I cannot hear.
Sorry that I don't see any. Yes, here. This, yes, the both. Does it depend on n? Okay.
Oh, okay. Ahora.
No. I wish. No. No variation. Okay? It may hold. I don't know. We don't know how to prove it, but no variation. How much time do I have? Okay. Okay, no, it's enough. So I'm going to tell you some ideas of the proof, of how you prove this. Okay, some flavor of what you do. And I'm going to restrict to the very basic case where my shift is the full shift. If I have a full shift for finite time, everything that I'm going to say doesn't work. There is another proof, another level of complexity to doing this. Okay? But this gives you the idea. So typically, what you do if you want to prove some limit theorem is you fix some potential and you define the following operator, the transfer operator. For us, it's going to be E a la f of 0x, phi of 0x, plus E a la f of 1x, phi of 1x. So you make the sum in pre-images, okay? And the most widely used method to establish the central limit theorem uses that if you take a Helder function, then L restricted to that space has what is called a spectral gap. It doesn't matter what a spectral gap is. It's an spectral property, but right away gives you, so by looking at the spectrum of that operator, you obtain the central limit theorem, if you like. Now, for Bowen observables, this is in principle of no use. It's not clear that Bowen functions are sent to Bowen functions. And even if that were the case, it is unlikely to obtain a spectral gap because you don't have regularity. You know that the spectral gap in the continuous function already doesn't have a spectral, the transfer operator in the continuous function already doesn't have a spectral gap. So you need a different proof. So let me assume that the measure is Bernoulli, 1/2, 1/2. And I'm going to consider the normalized transfer operator is just, I'm going to divide by 1/2. So F is minus the log of 2, which happens to be the entropy, right? Log 2 is the entropy. And I do this because I want to send the one function to the one function. So I'm going to say that it's normalized. It has this property, which is called the transverse property. So if you do L, if C composed with T and multiply by phi, you get C times the transfer operator in the second function. And this tells you that this is essentially an inverse of the Koopman operators on the left, because L of 1 is equal to 1, so you put 1 here and you obtain this. The third property, which is related to this, is that this measure is invariant. By the action of the unjoint, this guy, you can act like this if you like. So I want to tell you what I do with a measure in a function. And this is doing that. And then this is a little bit more complicated, but not too much. So if you do, again, I have a typo here, but I'll tell you what it is. Ln of phi composed with T of n. So you do it backwards, and as you do it in this case, is the conditional expectation of your function in T LF minus n, no minus 1. It should be say minus n. The correct formula there is the following. It's minus n. I'll tell you in a second remind you in a second what is this conditional expectation. But you see, if you do first compose with t, and then you apply the operator, you obtain the identity operator. And here, if you apply first the operator, and then you compose with t, then you obtain this. Let me remind you what that means. If I have a partition by cylinders, the ones that I talked at the beginning, the words of size n, I can look at this. This is a partition because each point is precisely in one word of size n, which is the beginning of its, the beginning elements of it, I guess. So it's a partition, and you're going to this conditional expectation, which is going to tell you the following. In a point x, this is a function, which in a point x, you get one of the measure of the cylinder, and you integrate the cylinder, the function on the cylinder, then cylinder. So this is the same, if you think a little, this is the same of the sum in all possible words, 1 over the measure of the word, and then integrate your function in that cylinder, and you multiply by the characteristic function of the cylinder, okay? And similarly, if instead of putting this, I put a finite partition, I get the same. For example, I could put these partitions, t minus 1 of n. And then I can compute the conditional expectation in this sigma algebra now as this limit, okay? Everything here is very basic. This one requires a theorem, but okay, believe me that this is true. So this is a way how to compute the conditional expectation. Now, this is a very simple computation which doesn't work except in this case, but okay. So if I take a word of size n and I apply L of n to the characteristic function of the cylinder and I evaluate in a point x, it's very simple to see that you get 1 over 2 to the n. So this is applying the operator n times, so you get 1 over 2 to the n, and then you put all the words before the point that you are doing, but you are evaluating the characteristic function of some fixed cylinder. So this only happens with k is equal to w, and then you get 1 over 2 to the n, which is exactly the same as the measure of the cylinder, w. So if my integral has mean 0, and if I do L of n of this conditional expectation, I apply this to the characteristic functions, and then I have the sum of I. But this over this gives you 1, so you end up with the sum of the words of size n, and you integrate it to some function over all these words, but this is a partition. So what you are doing is you are integrating the sum over the whole space, but this is 0 because the integral is 0. So that tells you the following. If I look, for example, of a L2 norm of Ln of Sn of I, this is less than equal to adding and subtracting the corresponding conditional expectation. This one, we saw that is 0. This one is bounded. And this is bounded because of the following. S of n is very close to n in a cylinder of size n. The variation of this is bounded. This is the condition that sums do not diverge one to the other. So it was the original condition or the Bowen condition. And this LFN is an operator that sends 1 to 1, so this remains bounded. So what you get is that Ln of Sn of phi is bounded in L2. Just by that simple computation, you get that. Now, if I have a function, a sequence which is uniformly bounded in L2 is weakly compact. So I'm going to take L of n of s phi, Sn of phi, and I'm going to make the average. This is also weakly, it's uniformly bounded because it's an average of something which is bounded. And you take a weak accumulation point, which exists by compactness of this sequence, and then you do a very simple computation. It doesn't matter that much, but you are going to get the following. You are going to get that the limit in L is L minus L of 5. So phi plus L minus L composed with T is in the kernel of L. Recall that L of this gives you L. Okay? So you get that your function is homologous in the usual sense to an element of the kernel of the operator. So what I have is that if I have a Bowen function of integral 0, then I can make it homologous to an element in the kernel. Okay? And I can do it in L infinity if I work it a little bit here. Okay? So any Bowen function is homologous by a L infinity transfer function to something which is in the kernel of the operator. And then I'm done. So this is an easy computation. If you look at the Sn of 5, this is the same of sigma square of C, which is just the norm of C. There is no correlation for that because it's in the kernel. And then I can use the representation theorem and says that the norm is 0, the variance is 0, if and only if this guy is a coboundary, because it's bounded, is 0 if and only if that limit gives you 0. And this is equivalent to this function to be uniformly bounded in L infinity. This is part of the representation theorem. So if it is not homologically trivial, so you have this computation tells you that this is 0, and then the sum with respect to this sequence of sigma algebra is what is called a reverse martingale. It doesn't matter, I have some theorem that I can apply directly there and I can finish the problem. This is Brown's central limit theorem, and this tells you that the central limit exists, and then you have the similar statement for phi also. Okay? So the thing is, this part is a little bit more, I don't know. It's not terrible, but it's a little bit computationally more difficult to see in the blackboard. What I'm saying is, you give me one of this function, I can make it homologous to an element in the kernel of the transfer operator. And then the whole thing goes. Okay? How much time do I have? Do I have time? 3 minutes. Okay. Do you have any questions? Several. Okay. So I'm going to be very quickly here. Okay? So I'm going to try to give you an application what this tells you. There are some words which I'm not going to define. This will make sense to some people, some others, perhaps you will be interested in learning what it really means. Okay? So if I have this part is easy, if I have a group, I'm going to say that a quasimorphism on the group is just a function from the group to R, such that if I make L in the product, this is at bounded distance to the sum of L of each element. So a morphism will be this number is 0. L of the product is sum of the L's. A quasimorphism is bounded distance to the sum. And I'm going to assume that my group is hyperbolic. If you like, you can assume that gamma is the pi1 of a compact hyperbolic manifold or compact hyperbolic surface. I'm going to fix some generating set, and I'm going to consider the corresponding word metric to that set. For n, I'm going to look at the elements which have size n with respect to that word metric. And if I have a rate in the Kiley graph of the group, I'm going to look at the initial segment of size n. Since the group is hyperbolic, this has a well-defined boundary, and I can look at the point that any rate determines, and I'm going to call it class of R. So this is what you get. So assume that pi is non-elementary hyperbolic, it's as say pi 1 of a hyperbolic surface, compact hyperbolic surface. So you look the measure, a particular measure, which is the Patterson-Sullivan measure in the boundary. And if you have an unbounded quasimorphism, which is a very irregular element, this tells you the central limit theorem for the quasimorphism. And in fact, you can do it point-wise. Okay? So if you look at the Patterson-Sullivan measure of the regions in the boundary, so you fix the initial conditions, say the identity, and you want L of Rn over sigma n less than C, this converges to the normal. And if you can do it with the points which have size n, it also converges to the constant. Okay? This is an application, it's a geometrical application of all this, and this is our main interest. So this is why we get Bowen functions. These guys are the quasimorphism in that group. The group is something discrete, right? It's going to be very regular. So we want to obtain statistical information of that irregular elements, and that's why we have to work with weak Bowen functions. Okay? And that's all. Thank you for your attention.